Okay, so hi everyone. Today I'm going to talk to you about Mylobot and detecting the undetected using deep learning. First, I'll present myself. My name is Yael Daihes, and you can see my picture here, but you can also see my face. And I'm a security data science team lead for Akamai Technologies, and I'll explain a little bit about this in the next slide. And I wanted to get to know you guys, but I can't see you guys. So I thought I'd present myself a little bit in a personal way. So during this pandemic, I think my days usually consist of all of the things that I listed here. So it's botnets, traffic, data, algorithms, and I also like reading, painting, and I also enjoy a little bit of gaming. So I hope this gives us a little bit of a personal introduction. And now let's talk about my daily work, or why am I here speaking to you. So I work for a company called Akamai, and maybe some of you may know, but Akamai is probably one of the largest CDN providers in the world, which means that they have a lot of servers all over the internet, all over the globe, and a lot of the internet traffic in the world go through Akamai. And over the years, they have transitioned into using all of this data into really interesting security product and defense systems. And specifically, I have the privilege of researching over this sheer size of data, like it's huge DNS traffic that we see every day. And my task is to look for attacks over this traffic and block it for everyone. So as you can see, I have great responsibility and also great visibility to understand how things look for about a third of this world at every given time. So we've established what I have is a DNS empire and a lot of data, but what do I do with it? So what's going to be on the agenda today? First of all, we're going to talk about Mylobot, right? It's an unknown name, at least it was for me. Let's get that out of the clear. And then we're going to talk about DGAs and how did the defense system and the defense community tackle this problem so far. We're going to also cover how did we at Akamai tackle this issue. And we're going to present you a real production system that we have running on real traffic at any given time. I'm going to share with the results in the wild, and then I'm going to give a really deep dive into Mylobot from our perspective. So what is Mylobot? Back in 2018, there were a few blogs about this new botnet that is on the horizon, and it's just now being discovered. And there was a few blogs by a few vendors here. You can see Trend Micro and Deep Instinct and CenturyLink and Morphisec and so on. And you can see there was some traction around it. And specifically, I took a snapshot of the blog given by Deep Instinct, and they were talking about how advanced this new malware and botnet is, that it has tons of evasion techniques. You can see anti-VM and anti-sandbox and anti-debugging and code injection and process hollowing, so many fancy techniques. And lastly, it also uses a DGA. Now, specifically, I'm focusing on this one because this is an evasion technique that could be visible in the network space, which is obviously my expertise. So I want to go over this specific evasion technique and walk you through our detection system to understand how we detected this really sophisticated botnet. So let's go over the basics. Say you were successful enough as an attacker and you managed to get your client, your malware, installed on a remote computer. And here you can see it on the left. And once this computer wakes up and the malware wakes up, you want it to do something for you, for your malicious intent. And you form some kind of command and control channel to have the ability to transfer data between the malware and the infected computer, and specifically in this case, between botmaster.com, which is the domain that is used for the command and control channel. And defense systems natively and naturally look for these command and control domains in traffic, or look for them before traffic happens. And they add this to this blocking system that would not allow the communication to pass through. So from the network perspective, the computer might be compromised, but it's not going to be able to form this command and control communication channel, and therefore the malicious activity is somewhat blocked. So what is a DGA? And the DGA is an acronym that stands for Domain Generation Algorithms. So specifically in this case, an attacker, a sophisticated attacker, understands that they want to evade the technique that I just showcased you. They want to evade the fact they have a one-point failure with the communication channel, and they want to be resilient to this. So they understand they want to create multiple domain names that could be potentially used for forming this communication channel. And what those sophisticated attackers do is that they write code just like you and me, and they add it to the malware. And this code generates randomly generated strings that could be used for those domain names. And those randomly generated domains are not completely random because they are based on a shared secret. And this shared secret is known both to the malware and to the attacker on the server side. So what happens on day one? The malware wakes up, the attacker wakes up on the server side. They both run this DGA code, the same code, with the same secret shared between them, and they're able to create the same chain of random looking domain names. And because they are so random and they look so gibberish, it's not very likely that they are registered to anyone. So the attacker can basically choose one of this really long list of domains and register it that day to an IP that belongs to their infrastructure for attacking. And for this day, this is going to be the communication channel for command and control. Then on day number 2, the same thing happened. The attacker and the malware run this DGA code. They create the domain names. The attacker registers only one of them. And this way, they are forming the command and control communication for the second day. But for your keen eyes, you will see that on day number 1, it was a completely different domain used for this communication. So for me, for the defense side, if I'm able to detect it or maybe predict it in advance, maybe I will be able to stop it. But during the day that this is happening, I need to detect it basically a few minutes later at most to be able to effectively stop this botnet from working, because otherwise tomorrow, this domain is not going to be relevant anymore. So far we understood what is DGA and what is this evasion techniques that attackers use. And I think I'm trying to give you a notion of what the solution for detecting this is going to be. It has to be timeliness, right? Because we want to be effective, but it also needs to do something with this really random looking pattern and so on. So this specific technique, as I mentioned, Mylobot was using. So how did the defense community tackle the DGA problem so far? So this is an example given from a blog and a GitHub from a researcher that I really appreciate, and I would like to give a shout out to, and he's called Badr J. You can see the link here at the top left. So usually what researchers did so far is once they got a hold of a malware that has a DGA code, they just reversed it. And once they reversed it, they found the piece of code that is the DGA, that is generating these domain names, and then implemented back in Python, for example, just so the community can use this to predict the domains that are going to be used tomorrow, next year, next week, whatever. So this is an example of a real case of a quite an old malware called Cinda. And this is a real reverse engineering task that he did and re-implemented it in Python. Now, what can the defense community do based on this reverse engineering? So, as I said, these domains are basing their creation of domains based on a shared secret. And sometimes this secret is also called a seed, is something that is not that trivial to achieve or to retrieve back from the code. Sometimes it's not even in the code. So using this reversed code, what defense community did so far is try to leverage it for, first of all, breaking the seed. For example, if I see a lot of domains in traffic and I see that the pattern looks like something that could be generated by this code, maybe I can brute force this and then understand the seed in retrospect, for example, and once I have the seed, I have the ability in combination with this code to create all of the domains that it's going to create tomorrow and next year. And another thing we can do is that sometimes there are domains, there are DGAs that don't use a seed, and in which case this is a problem that is already solved and it's really easy. So this is most of the work that's been done before what I'm going to show you, and it's really valuable, right? Like, it's spot on. We have malwares and samples. We know how to reverse engineer. We know how to get what we want. But there's an inherent problem with this specific solution. And I think you would all intuitively agree that how can it detect anything new? Like, this is a system that we built to detect the same variant or the same malware family that we already know. But what about if there's a new malware on the horizon and it's using a DGA? Can't I leverage my knowledge of this very interesting phenomena to detect it without being it's based on the binary and reverse engineering? And also, if I already managed to retrieve the malware and I have the binary at hold, what about if I couldn't break the seed? So it means I have the code, I have the reverse engineering, and still I can't block it in traffic. Like, I can't predict what it's going to use tomorrow in advance. It's mind-boggling, right? So for advancing our defense system, we're gonna go through a thinking process together right now. And our goal is, first of all, as I just stressed, we want to be able to detect DGA domains that we couldn't break. Because if I have the malware, it's pretty ridiculous if I couldn't block it in traffic tomorrow. Secondly, we want to be able to detect new malwares using DGA, even if I have no knowledge of the pattern, no knowledge of how it's going to look in traffic. And a bonus goal would be if I'm able to detect the ones that I did break and do know, because then this would make my new system a holistic system for solving a DGA-based malware. So this is our goal. And now let's go through this together. My first intuition, and I hope that yours as well, would be, okay, this looks pretty gibberish, right? Like, if I look at the domain names in traffic, it looks like something that wasn't generated by a person. Nobody wrote and typed it in, and it looks pretty weird, right? So can't I just make a heuristic or basic algorithm that would understand this exact intuition? And this exact intuition is quite true. And the way we formulate it in a statistical manner is we say that we believe the distribution of characters used for the domain name is not going to look natural at all. For example, you can see that this is a real example of two malwares. And you can see that the distribution or the amount of characters used in the domain names look very interesting. For Timba, for example, you can see a uniform distribution between characters A and Z, which means that every character used the same amount of time over the language. And obviously, this is something that is very different from natural language or for domain names that are popular, because, for example, we can all understand intuitively that vowels are used much more than every other letter in the English language. So obviously, it's not going all to be for the same frequency. And for example, for the Dyer malware, you can see that it uses the same characters for hexa, which is obviously something that we're not using natural language. So when you see this, you're thinking, okay, so this is a really easy way to understand that all of these domain names are coming from malwares. But attackers are not dumb. Attackers adapt. Like, they understand that we're looking for ways to block them, and they understand we're looking for ways to detect them. So they just adapted. And what they did was they basically created the domain names in the code, but they're sampling or using the characters for the same distribution that is in Alexa top 1 million domains. So obviously, the heuristic that we just had and which we tried to create together wouldn't work. But okay, wait, hold up. Like, we're still smarter, right? We are working just as hard as the attackers to try and defend our system. Like, okay, we got this. So what we did next was, okay, I'm going to look at the distribution of the two characters in the language, which means that I'm taking every two characters concatenated and looking how frequent that is in the domain names. And here again, you can see that I was able to differentiate between domains that are coming from a DGA code and domains that are coming from Alexa. But again, attackers adapt, they understand that this cat and mouse game, they always want to win. And this is an example of an even newer version of a DGA code, and it's sampling also from the distribution of the two characters. So you can see this cat and mouse game is quite difficult for solving this issue. And this pretty much got the research community to understand that we need something better, we need something smarter, we need something stronger. We need something that would understand the pattern and not only the difference in pattern. So this intuition and the fact that we need something stronger brought the research community to understanding that we need deep learning. And specifically, deep learning or a neural network model, and the neural network that was used here is called an LSTM. And its specialty, or it's made for understanding sequences. And we were hoping that if we input it with enough example sequences of both domains that are used, generated by DGAs, and domains that are used in traffic, it would understand the inherent difference in pattern between those domains and the benign domains. And what it essentially means is we were hoping that the neural network, by seeing a lot of examples, would essentially understand the regular expression that is describing these pieces of codes. And this is a really profound understanding. Like, we went from having a heuristic and some kind of boundary to decide between this question to something that we want to actually understand the pattern. And this notion was first portrayed by an academic paper that I shared here by Endgame, a company called Endgame. And it was really interesting to see because their idea was quite interesting, but one of the things that we faced at the time was, okay, but there's a bit of a distance between having this intuitive solution and maybe writing an academic paper about it and actually having it in production running on this massive amount of third of this world traffic. So let's see how we use this intuition and all of the progress that research have done outside of Akamai and took it in. So what we did is that we used this architecture, as I just showed you, of the LSTM neural network, and it needs to have a lot of data and a lot of examples to learn from. So we built a data set, and we built a data set of 1.2 million domains that were created by DGAs. And the way that we did that, for example, is by actually taking samples of malwares that we know have DGAs and using them to create a lot of names. And I gave her another example because I would encourage you to do something very similar, is there are open sourced databases that you can grab and use for this kind of research that has a lot of domain names. And I gave an example to a great one. And on the other hand, we want the network to understand also what is the pattern that it's trying to differentiate it from. Like, we wanted to be able to understand that this is a DGA, but also that this is a benign domain. So we also feed it with 1.2 million benign domains. Now, back at Akamai, what we did was to just grab normal traffic and add it to the data set. Obviously, not all of you have the access that I have, but hopefully you all know what is Alexa top 1 million domain, which is a list providing the top 1 million domains seen, used in traffic. And this could be a pretty good data set to use for the benign examples here. So this is the data set we built. We run the neural network, we train it on this data, and we achieved great accuracy. Like, the network learned the difference between DGA and benign domains. But one of the misfortunate, or one of the shortcomings of the result of this neural network was that it wasn't able to classify which malware family it came from. And now I would like to stress out why it's important to us. As a defense community, it's not enough to only block it in traffic. I want to be able to provide the person I blocked it from with actionable intelligence on what is the malware that you are infected with. Like, what is the malware you need to mitigate? And I was hoping that when I'm using such advanced system that understand the inherent pattern, it would also understand the malware specifically it's coming from, because it learned a pattern that belongs to this very specific code. And once we saw this result, we were quite disheartened because we really wanted to solve this issue. And we are going to solve this issue together again. But first, we needed to understand, why is it such a difficult task for the neural network? Now, this is probably the most mathematical slide I have in this presentation, so please bear with me. But I tried to get an intuition of why is it so difficult for the neural network to understand which malware it's coming from. So what I did is that I visualized all of the data that I gave the neural network, and I visualized it in a way that I wanted to see each and every domain in the data set. Where does it fall in the space that the neural network is making a decision on? So intuitively, if you guys were the neural network right now, and I would tell you that the green cluster here, for example, is the benign domains, I think we can all understand I can draw some kind of circle that would say, okay, this is the benign area and everything else is malicious. So this is why it was so accurate with understanding if it's benign or malicious. But this visualization also explains why it was so difficult for the neural network to divide it between the different clusters. You can see that some clusters are already separable, and it's really easy to understand that this is, I don't remember the colors, but this is a KDARs and this is RAMNIT and so on. Maybe it's separable enough. But you can see that some of those clusters are too intertwined. You can see that, for example, at the cluster at the top, you have purple dots and blue dots and red dots and brown dots. And obviously, if I, in my human eye, can't pass a line or a circle to differentiate between the clusters, the neural network couldn't do that either. And the intuition behind that is that it's true. They are not separable by regular expression. They are not separable by pattern. They are all DGA domains or DGA code pieces that generate domain names that follow the following pattern. Random choose a character between A to Z, 7 length of a domain name. So obviously they all have the same regular expression. So I understood that my intuition and using this neural network actually worked, but this task is just not solvable by a neural network. But while viewing this and understanding that this is what's happening, we saw, okay, maybe we need to go for something simpler. Like, we have this understanding that these are all represented by regular expression, by patterns. Maybe we can leverage that to using an aftermath, maybe, and understanding which malware it's coming from. So after this whole thought process that we did together, I'm going to showcase you the actual system that we built that is actually running and protecting me and you and all of you all over the internet. So what we did here is that we took our live system, our live DNS traffic, and we divide each user into a very small specified time window of DNS queries that we see. So here, for example, you can see that the user is querying facebook.com and maybe google.com with a typo here. And you can see funny looking domain names that you and I by now understand that it looks like a DGA, right? It looks very weird. And what our system does is that it takes all of these domains that are coming from this time window, which could be both the malware querying and the user querying because it's using their computer. And we use our neural network to decide if this domain name is looking like it's coming from a DGA code. And we ask the neural network a very simple question: is this a DGA or not? And it gives us a result between 0 and 1, where 0 represents, nah, it's not a DGA. And 1 represents, yeah, this is a DGA, you need to block this. So here you can see, for example, and this is real results actually, that on facebook.com, the network said 0, it's not a DGA. And here you can see on 2 other domains, it said, yeah, it looks like a DGA. And for the typo, it said, no, it doesn't look like a DGA expression. It doesn't look like a pattern. So you can see the results here. And then what we do is that we take all of the domains that pass this threshold of understanding, okay, this is a DGA. And then we try to attribute it to the specific malware. We take it as a group and we try to fit it to all of the regular expressions that we already understand that are belonging to this specific DGA code. And this is quite novel. Like, this is something that I'm not aware that anyone has been able to do before us. But using the system and using the fact that we have it coming in from traffic, we were able to attribute so many detections that we are making. And moreover, it's so cool because we were also able to detect and even group together newly seen DGA domains, because what this system essentially is doing is not only detecting the fact that it's coming from a DGA, but it's also saying, and this is the shared pattern that all of these domains share. And is it something that I already know, or is it something that I don't know yet? I'm not sure, but I'm going to tell you in a second. And you can see that in some cases, we were able to attribute, okay, this group of domains is 100% fitting for the Locky pattern, so we're going to label it as Locky. And another case for dire. And for the case that it's a regular expression that was never seen before, we're going to give it a name, unknown number 1. And this is really cool because this way we can track this newly detected malware over time. And at one point in time, when you or every other researcher is going to share your blog and share with us some newly detected malwares, we can attribute it and give the story of this malware over time because we already detected it. Now, if there's a question now, and I hope some of you might think it is, okay, but why can't you attribute it or give it a name, or why don't you research it yourself? You need to remember that as Akamai and the standpoint that I'm standing in, I don't have access to the endpoint. In many cases, all I see is the network, and I maybe control and own the network, but I can never go to the specific computer and then grab the process that is generating these queries and then research it and then give you guys this whole new, listen, this is the new testament or whatever. But as you understand, from a network point of view, it's going to be called unknown until one of your reversers or endpoint security researchers is going to tell me what is the name of this malware. So this is an actual system that we have predicting on actual traffic and blocking it on real time. And I want to share with you actual results. Now, this is running in our systems for, I think, maybe about a year. So the result in the wild is that we detect and we block daily about 2.5 million domains, which is huge. And because of that, we block about 70 million DNS requests a day by this system alone. And this specific number is subtracting Mylobot, which we're going to see in a second, because you'll understand that Mylobot is going to skew these numbers way to the other end of the scale. Now, the system has a very low false positive rate. And the reason is not because the patterns in the system is so good, it's because also as part of putting the system in production is adding a lot of understanding of how we need to enforce this and how we need to filter this. So we have a lot of algorithms that I didn't go in that we do to make sure that we have no mistakes, but to make sure and also to rest assure you, I will not have any intention of blocking anything that would affect you badly. So it's really important for me to have 0 false positives, because otherwise I would block something that you all use. And lastly, as I showcased, we have a lot of unknown groups that we track over time. And it may be a 0 day, it may be a malware that nobody reported on yet. But for our point of view, we are certain that this is a process that is using DGA code. And it's our task to attribute it, to understand, is it a malware? Is it maybe maybe a VPN using this evasion technique and so on? But we are definitely tracking all of these to understand their activity. And now we're gonna dive into Mylobot. So I hope that so far you understood our system and what we're doing. And one of those really interesting detections is called Mylobot. And as I showed, there was some blogging about it back in 2018. And based on these blogs, I wanted to go over how they reported it as using, so I can explain what we saw in traffic. So this is based on the report done by Deep Instinct and CenturyLink. And the first stage of Mylobot action or a traffic communication pattern is that the client, the malware, is querying a regular DNS query. And I think that by now you should all have this like red flag and saying, okay, DNS, this is probably your expertise, so you're in the right direction. And the DNS is replying with an IP that the client needs to query next. Then the client queries this IP and is asking, where do I go next? Now, this IP is already the attacker's IP, and they're just serving them with the next server they need to go in order to download a second stage malware. So then the client goes to this very specific IP and server that the former server served them, and they're getting in return a new type of malware. And for the last stage, it's unknown activity for my end because I'm not sure which malware they are downloading. For the reported cases so far, they have used a second stage malware called Khaleesi, but obviously we all understand it can change because this is a classic downloader scheme. But what's not classic about it is the first stage and this really funny looking domain name. And this is what we're going to focus about and what our system is going to detect. So what did we detect in traffic? All of your smoking guns pointed correctly. We detected this very funny looking domain name because it looked like it's coming from a pattern that is a DGA domain generated. And we detected about 1,400 domains that are coming from this operation. And the specific pattern that we understood coming from traffic is this pattern written right here. It's the prefix letter M, and then a number between 0 and 43. And then this is for the subdomain. And then for the domain part, it's a domain generated by a DGA, a very specific regular expression, and then one of those TLDs. Now, this is exactly as reported by CenturyLink in their blog about a year and a half ago. But wait, is it everything that we detected? No. We actually detected much more than that. But we understood that this is Mylobot because we saw the blogging on some of the detections that our system made. Now, what we actually saw and the system alerted us on is actually what we understand to be 4 different variants of this specific botnets. And we actually detected about 8,000 domains that are all looking for a very similar pattern. And I gave the example of the patterns here. So you can see the variant number 1, we call it the M variant because it's the prefix M. Then for the second variant, it looks exactly the same like the M variant, but the prefix is the letter X. So we call it the X variant. Then for the third variant, we saw something a bit different and interesting because it starts with the prefix and the word green, and then the numbers, which is a bit different, but we call it the variant green. And lastly, we saw a variant that is prefixed with the letter V and the number 1. We didn't see any of the other numbers 0 between 43 like the others. And what's interesting here is that once you understand my system, and you understand that all of these queries came somewhat together. And my system decided that they are all fitting the same pattern. And this is why I'm going to attribute all of them in the name unknown number 56. I don't know what number it was. But once I saw that and I saw the blocking, I thought, okay, I need to understand this more. Like, is my system making a mistake? Are they really connected? Like, is it the same malware? Like, am I sure that this is the correct detection, or is it a mistake by design? So what we did at the time, and this was the beginning of 2019, is that we decided to take the domain names that we saw that are actually resolving in traffic, meaning domain names that the attackers actually registered and used for communication for command and control. And we wanted to see if there is any connection between the variants. And again, may I remind you that I don't have any access to the endpoint. So all I can do is the network research and everything from the outside. So this specifically screen, what you're seeing here, is a map that we created using VirusTotal Graph. And every time you see a blue globe on this map, it means that the entity we're looking at is a domain or a subdomain. And every time you see a flag in this graph, it means that it's an IP and the flag represents the autonomous system it's coming from, originating from. And what we saw here was really cool. You can see here on the left, 2 domain names that were resolving for the M variant. And I also added the subdomains here so you can see that the pattern that I'm reporting is true. And you can see a lot of queries that are reported by VirusTotal to this specific pattern. And you can see a lot of IPs that they are resolving to. But what was interesting in this case is that here on the right, you see the domain that was resolving at the time for the X variant, and you can see that they're resolving to the same IPs. And in this case, we're thinking, okay, so they have to be connected, like they're forming the command and control communication with the same IP infrastructure. Another interesting thing that we saw, again, back at the time, was this Portuguese flag or this Portuguese IP. When we tried to research further and understand what's standing behind those IPs, and in the hopes of understanding the attacker, we realized that this might be a company, a cybersecurity vendor that is trying to sinkhole this. And this makes a lot of sense, right? Because as I said, back at the end of 2018, they were blogging about finding this M variant. So it makes a lot of sense that the M variant domains are resolving to this specific IP. But as you can see, as we understand it, the sinkholing efforts didn't work quite well because the malware is still managing to create a command and control communication channel through other IPs. And I think that it means that maybe this operation of the M variant even continued further. But then we went even further. We understood that there is a connection between M and the X variant. What about the other variants? And again, we saw the same thing happening for the green variant and the M variant. Again, they are resolving to the same IP, and they're also resolving to other IPs, but you can see the connection here. But another thing that was interesting here is this variant that we saw that looked a little bit different, but again, my system decided they're all grouped together, that is called the V1 variant. And there were 671 domains that were all resolving to, again, our favorite sinkholing effort, the Portuguese IP. And from what we understand and our working theory is that the V1 variant is actually the earliest variant of this botnet and was maybe some kind of toy variant. And this was already successfully sinkholed in the past by this company. But you can see that the other two variants are still much working and managing to communicate. Now, coming for this presentation, I wanted to give an update and I wanted to see how does it look in traffic. And as I mentioned, my system is fully automatic. If there are new domains, it's detecting it and it's adding it to the pattern, it's calling it Mylobot in the appropriate group. So I just needed to do this kind of analysis again. And this is the map that I pulled, I think, maybe a few weeks ago, specifically for this presentation, 2020, of Mylobot infrastructure. And wow, first of all, you can see the size change and how large it is now, because I think maybe it indicates how enthusiastic Mylobot attackers are right now, because you can see a lot more resolving domains and a lot more IPs and a lot of things going on here. So what you can see here, again, 2020, there are new resolving domains and the operation is still much in the works, and you can see the connection between the two variants again with a lot of resolving IPs. You can again see the Portuguese company trying to sinkhole this, but I'm not sure that it's that successfully. But another interesting thing that we decided to do for this analysis this time is, okay, we wanted to see if we can find the communicating malicious file. So what we did here is that we saw a lot of files that are communicating to these IPs, and you can see that there's a lot of shared communication between all of these IPs for these files, which is the M variant. But there are two interesting cases here. You can see at the top that there are two files here that are communicating to an IP from the M variant and the IP from the X variant, although those IPs are completely different and not shared. So maybe this is representing to a file that is the same malware, but with different configuration, it's running either the X variant or the M variant. And for the same case, you can see here at the bottom of the map, another two files that you can see communicating to an IP for the X variant and for the M variant that are not shared. So we are feeling pretty confident with the connection between all of these different malwares, especially because our system made the connection, but it was really cool to see it from the network perspective that, wow, this is a really interesting and increasing issue. And then we wanted to look how it looks in traffic. So I wanted to give you some intuition and understanding of how things look when you own such a huge DNS empire. And here what you can see in this graph is that you can see the amount of queries done over a network to Mylobot CMC domains over time. And just to make sure that you're all noticing this correctly, the Y scale here is in billion requests a day. It means that at the lowest point that we are at right now, there are 0.2 billion DNS requests a day made to Mylobot domain, which is 200 million. And for comparison, I wrote the amount of queries that we see daily to other really well-known and prominent botnets in our traffic. So PikeSpa is the next best, I don't know if to call it best, but is the next most prominent botnet on our network. And we see about 1 million DNS requests a day. And then for QSnatch, we also see about 1 million requests a day. For Emotet, 500,000 and so on. So you understand that this is 200 times more traffic than we see from the other botnet. So this is a really noisy botnet. And then we wanted to try and understand, okay, so how many infected users are there in the world with botnet? And this is only coming from understanding the traffic patterns. Now, what you see here is the amount of entities that we see communicating to Mylobot CNCs over time. Now, I would like to point out that when I'm saying entities, it could be either a single user and their whole computer, but it could also be a NAT. It could also be some kind of enterprise or corporate gateway, which means that a single entity, from my point of view, could represent tens of thousands of computers. So this graph could actually be much higher, and this phenomena could be much prominent that we actually understand it. And even though we are masking some kind of the user that we're seeing, you can still see that back at the end of 2019, we had about 3,000 or 4,000 infected entities. And to our understanding, currently what we're seeing is between 7,000 and 8,000 infected users. Between Mylobot managed to double their infected users over the course of this almost last year. So even circling back to the question that I was asked for the warm-up, here you can see the evolution of this botnet and how fast it was able to spread widely. So far we've covered a lot of things, and I wanted to touch base on every single thing I shared and then share with you some takeaways from this. So first of all, I hope that you all understand what is DGA, that it is a piece of code that some malwares have that generate domain names for CNC channels. Secondly, I shared with you our defense system that we actually built and we're actually using on live traffic to detect the domains and then block them, and that is based on a deep neural network, and that is not something to be feared from. And lastly, I shared with you our most interesting detection so far, that is this botnet called Mylobot. And I shared with you how prominent it is and how super active it is, and that you all should look out for it. I hope that your main takeaways from this is that, first of all, there are countermeasures for Mylobot. As I just explained, by monitoring DNS traffic, we were able to detect it and then block it effectively. Secondly, I will publish all of those IOCs that I see, and I will share a blog that you can all touch base with, but I would encourage you that using deep learning and not being fearful of that gave me at least the power to build this beast of a detection. Like, it's blocking by itself and doing phenomenal work. And lastly, even though reverse engineering is probably a hobby for a lot of us, the threat intelligence and the network perspective was really interesting here, and we were able to get really interesting results by only investigating the patterns, the new domains, and then researching them back on some open source platforms. That I would encourage you to do the same. But on the same note, if any of you is interested in collaborating about this and they've seen this malware, they want to talk to us, so feel free to reach out and touch base and connect with us, because we would love to share and help the defense community defense as much as possible from these threats. And if you see anything that is related to DGA, feel free to connect with us. And this is my my contact if anyone is interested. And I would like to thank you all for listening, and studio, back to you.